Hello, it's Stat 135, Lecture 5. You guys have Quiz 1 next Friday. It's going to have 3 problems, 2 problems similar to Homework 1 and 2, and 1 problem which will be a mom calculation. So last time we saw that mom estimates are consistent when h is continuous. Remember that a mom estimate is a function h of the sample moments, and since the sample moments converge in probability to the moments, that's by the generalized weak law of large numbers, then by definition of a continuous function, the method of moments, which is a function of our sample moments, will converge in probability to the population parameter, which is h of the population parameters when h is continuous. So, and that's pretty much all the time. So today we're going to cover section 8.4, and I'll show you an example of mom calculation, non-parametric bootstrap for 95% CI, and also how to compute the standard error for an estimate by hand. So for our mom estimate, this is a problem from Chapter 8, number 16a. Just first to review an important identity coming from the gamma distribution is the integral that's boxed here. So it's in your best interest to know that, because it comes up quite a bit and will help you avoid doing integration by parts. So consider an IID sample of random variables with density shown 1 over 2 sigma exponent of minus absolute value of x over sigma with sigma positive. Find the mom estimate sigma hat of sigma. So our distribution has a single parameter, so we're just going to need one moment. We'll try with the first moment, but we quickly see that the first moment is 0, because when we attempt to find the expectation, we see that the integrand is an odd function, and we're integrating from minus infinity to infinity. So then we're going to try the second moment, and now the integrand's an even function, so we can just simplify things a bit and integrate from 0 to infinity. And then we recognize, lo and behold, the integrand is the variable part of a gamma 3 1 over sigma, and we recognize what that integral is using the identity from above. So we just get that the second moment is 2 sigma squared. All of that's step 1. We've written the second moment as a function of our parameter. Now we invert things and write our parameter as a function of the second moment, and then we plug in the sample second moment for our second moment to give our mom estimate. Next, I'm going to show you how to do a non-parametric bootstrap and confidence interval for a population parameter. So the motivation for this is that sometimes you get your sample not by SRS, and sometimes your sampling distribution isn't normal. Those are requirements to do the sampling distribution the way that we did it in Chapter 7, say for a population mean. So I'm going to show you a way to do it just computationally, which will remove any such restrictions. So, but first let's derive a formula for what a 95% CI is. So we take our estimator, we subtract off the true parameter. So this is in some sense standardizing the distribution, the sampling distribution. And then suppose that we know this and we could find the 2.5 and the 97.5 percentile. So you could find A and B such that the probability that theta hat minus theta is between A and B is 95%. Then we just do some manipulation, some algebra here to get our 95% CI for theta, which is the interval theta hat minus beta, comma theta hat minus A, minus beta minus B, I'm sorry. So the problem is that theta hat minus theta isn't known to us because we don't know theta. So we're going to approximate by bootstrapping. Okay, so our estimate for theta is going to become our theta hat, and our estimate for theta hat, so we're going to call that theta star in what follows. So there are 5 steps. We're going to take a sample, a single sample of size n one time from our population, call that our original sample. Then we're going to resample from this sample, say 1,000 times, with replacement size n, so the same as the original sample, and we're going to compute the sample estimator of theta. So for each of these, we can compute the estimator for theta. So that gives us 1,000 estimators. Okay, so this is basically, so now we're going to subtract off theta hat, and this is going to be essentially our standardized sampling distribution, but it's from the sampling distribution from our original sample instead of from our population. So we have 1,000 data points, so you can sort them from smallest to largest. Take the 25th and 975th largest value from a list of 1,000 in the previous step, and this is an approximation to the 2.5th and 97.5th percentile of theta hat minus theta. Finally, the 95th percent CI, from what we saw earlier, that's theta hat minus B, comma theta hat minus A, where now theta hat is our original, so theta hat's our original sample estimate of theta, and A is the 25th largest theta star minus theta hat, and B is the 975th largest theta star minus theta hat. So that's how you do it in lab. You should have gotten some experience doing this in R, and we'll see why this works later. So finally, I want to talk just briefly about the standard error of theta hat. So theta is a parameter determining the distribution of x, and you can think of the SD of x, which is also written sigma. This is a continuous function of theta. So for example, if x is Poisson, the SD of x is the square root of lambda. So lambda is our parameter. So sigma of lambda is the square root of lambda. That's just a continuous function of lambda. So if sigma is a continuous function, then since our MOM estimator is consistent, theta hat converges in probability to theta, then sigma theta hat converges in probability to sigma theta. So sigma theta, which is an unknown quantity, we can approximate that by sigma theta hat for when n is large. So in other words, to find the variance of theta hat, we ultimately need to know theta, which we can approximate by theta hat. So just a quick example, say that you have an ID sample is taken and you collect data. So x1 is 4, x2 is 7, x3 is 4, x4 is 2, x5 is 3, and this follows a Poisson distribution. Find a MOM estimator for theta and approximate the standard error of your estimate. Okay, so what we're going to do here is the standard error of theta hat. That's the square root of the variance of lambda hat is the variance of lambda hat. Lambda hat is the sample mean, and the variance of the sample mean we know is the variance of x over n, and the variance of x, because x is Poisson, the variance of x is lambda. So now we can approximate lambda by lambda hat for the reason that we just discussed. And so lambda hat in this case is 4 with the data that we have. So an estimate for SE of theta hat is the square root of 4 over 5. It's exactly the square root of lambda over n, but the problem was that we didn't know what lambda is, so we approximated it. Just another word, you could have done this also by, instead of the variance of x, you could have used the sample variance. That would have given you another estimator, but actually it's a little bit more computationally intensive. So have a great weekend, and I'll see you next time.